signal. The expression for instantaneous voltage of Fm. Here we will give the representation for message signal as Vm of t is equal to Vm cos omega mt. Students, this is the same equation that we had discussed before in the previous video. So here Vm is the amplitude of the message signal, omega m is the angular frequency of the message signal, and that is given as equal to 2 pi fm, where fm is the frequency of the message signal. I number this as equation 1. Moving ahead, carrier signal is represented as Vc of t is equal to Vc sine omega ct, where again Vc is nothing but the carrier amplitude, omega c is the angular frequency of the carrier signal, and omega c is nothing but equal to 2 pi fc, where fc is the frequency of the carrier signal. I number this as equation 2. And the FM signal, that is frequency modulated signal, is represented as Vfm of t equal to Vc sine theta of t, where Vc is nothing but the amplitude of the carrier signal and theta of t is the angular frequency of the frequency modulated signal. I number this as equation 3. Now moving ahead. In the previous discussion, we saw that the frequency of the FM wave varies from a maximum value to a minimum value. We represented it as the frequency Fmax and Fmin. In either of the cases, either a delta Fc value was getting added to the Fc or getting subtracted from Fc. Accordingly, in simple terms, I have given the frequency of the FM wave as F equal to Fc, that is carrier frequency, plus or minus delta Fc. Delta Fc is nothing but the change in the carrier frequency, which in future we will be referring to as frequency deviation. So here the same expression can also be given as Fc plus or minus delta Fc. Now what I have done here is I have, instead of taking plus or minus of delta Fc, I have given a general expression as Fc plus something. Now this something could be the positive side of delta Fc or the negative side of delta Fc. This is nothing but a simple mathematical representation. So here I have given the overall representation for the FM signal as F is equal to Fc plus delta Fc. Now this delta Fc value could be a positive value or a negative value, but in this expression of F for the FM signal frequency, I have not mentioned whether delta Fc is a positive value or a negative value. In general, I am just adding it to Fc. In case if delta Fc is a negative value, then automatically it gets subtracted from Fc. And in our previous discussion, we also saw that this delta Fc is nothing but directly dependent on the amplitude of the message signal. So that means I can represent it as delta Fc is nothing but directly proportional to Vm of t, where Vm of t is nothing but the message signal, and that was represented as Vm cos omega mt. So I'm doing that substitution for Vm of t. So the equation now becomes delta Fc is directly proportional to Vm cos omega mt. The constant of proportionality I have taken as Kf. F is the subscript which indicates that it is the constant for frequency modulation. So here delta Fc is equal to Kf into Vm into cos omega mt. Now this expression can have a maximum value when cos omega mt takes up a value which is equal to 1. So at that time, what happens to delta Fc is delta Fc now becomes equal to Kf into Vm, because the cos omega mt value is now at its maximum value, that is equal to 1. So at this condition, whatever the delta Fc value we get, we represent it as delta Fc max. Reason why we are giving this subscript as max here is because the maximum value that cos can take up is 1. So at that condition, whatever the delta Fc value we get, we represent it as delta Fc max. So now delta Fc max is equal to Kf into Vm. So the frequency of FM wave can now be given as F is equal to Fc plus Kf Vm cos omega mt. Remember this equation which we had discussed as F is equal to Fc plus delta Fc. That delta Fc from here, this particular equation, I am substituting it in this expression. So I get the frequency value as F is equal to Fc plus Kf Vm cos omega mt. So this I am numbering it as equation 4. Now moving to the next slide. Students, we have already studied that omega of t is nothing but equal to d by dt of theta of t. This is a concept that you have studied in your physics. So we start from here and we do some small amount of juggling here. When you cross multiply, what you get is omega of t into dt is equal to d into theta of t. Integrating this expression on both the sides, what we get is integral omega of t into dt is equal to integral of d into theta of t. Now if you observe, at the RHS side, I have the integral sign, and along with that, I also have the differentiation sign. So they both get cancelled out, and when I swap the LHS and the RHS side, the resulting equation what I get is theta of t is equal to integral of omega t dt, or omega is nothing but equal to 2 pi f into dt. So I have done that substitution here for omega. 2 pi f into dt is the expression. Now, we have already previously seen that f is nothing but equal to fc plus kf vm cos omega mt. Here 2 pi are constants, so I'm just pulling them out of the integral sign. So this becomes theta of t is equal to 2 pi integral f into dt, and the value of f is shown here. So this f value we will be substituting onto this particular equation. So the resulting equation will be, please observe this equation which I have numbered as equation number 4. This was already discussed in the previous slide. So I've just put the same equation with the same number. Nothing new here. Moving to the next step. Here when I am substituting equation 4 onto this theta of t, I get theta of t as equal to 2 pi integral fc plus kf vm cos omega mt into dt. So the next step will be separating out the integral sign. So what I get is theta of t is equal to 2 pi integral fc dt plus 2 pi integral kf vm cos omega mt into dt. Now here students, I have taken out kf and vm, which are nothing but constants. So I've taken them out of the integral sign. So the resulting expression has a small change here. The only integral sign is applied to cos omega mt, whereas kf and vm are pulled out of the integral sign. So moving to the next step, we already know that Fc, which is nothing but the carrier frequency, is a constant. So that means I can also pull out Fc out of the integral sign. So integral dt is nothing but equal to t. So here for this entire first term, I simplify it as 2 pi Fc t plus 2 pi kf vm integral cos omega mt into dt. Now please think and tell me, what is integral cos omega mt? The answer is here. So integral cos omega mt is nothing but sine omega mt by omega m. So when I do this substitution onto the equation, what I get is 2 pi fct. Observe, I have changed this 2 pi fc as omega c. So I have it as omega c t plus 2 pi kf vm. These are all the set of constants here. I am just pulling them out here in the same way to the next step. That's it. No changes done here. Whereas the change is done here. Integral cos omega mt into dt. I have replaced it by sine omega mt by omega m. This is simple mathematical formula which you have already studied. So now on simplification, what I get is, see here, the omega m, I have replaced it as 2 pi fm. Reason is simple, 2 pi here gets cancelled with the 2 pi here. So from that, the simplified expression will be something like this. Theta of t is equal to omega ct plus kf vm by fm into sine omega mt. Here I am having sine omega mt by fm. That fm I have put it here. Moving to the next step. We know that delta fc max is nothing but equal to kf into vm. This we have already seen in the previous slide. So what we now do is, in the expression for theta of t, we will replace this kf into vm by delta fc max. So this is the equation that we discussed just a while ago. The same equation I have written here, no changes done in this. Theta of t is equal to omega ct plus kf vm by fm sine omega mt. Now kf and vm, this I will replace it by delta fc max. So the equation now becomes theta of t is equal to omega ct plus delta fc max by fm into sine omega mt. Now observe this highlighted term here. This delta Fc max by Fm, I will replace it by a symbol that is MF. So substituting this MF onto the above equation, I will get theta of t as equal to omega Ct plus MF into sine omega mt. Now what is this MF? MF is nothing but the modulation index for Fm. If you remember, the modulation index for amplitude modulation, that is for AM, the symbol we used was M with a subscript of A. Now here we are using M with a subscript of F, indicating this F as for frequency modulation. Now students, remember this equation which we numbered as equation number 3? Here actually we had defined the frequency modulated wave as Vfm of t is equal to Vc sine theta of t. And till now whatever the steps we derived, they are nothing but the representation for theta of t. So now our Fm equation will be complete when we substitute this theta of t onto this equation number 3, and we'll look out for any possible simplifications. So when we substitute, what we get is Vfm of t is equal to Vc sine omega ct plus mf sine omega mt. This I am numbering it as equation number 5. This equation, which we have numbered as equation 5, can be simplified using something called as Bessel's function. So using Bessel's function of first kind, when equation 5 is solved, we get infinite number of terms. And these infinite terms indicate that there are infinite number of sidebands in the expression. Only those sidebands whose amplitude is either greater than or equal to 5% of the carrier amplitude alone are considered as significant sidebands. Now students, here this is one of the possible target for 1 mark questions. Define significant sidebands. So the definition is the sideband whose amplitude is greater than or equal to 5% of the carrier amplitude are considered as significant sidebands. Before we could get into the expansion of Bessel's function, we will just look into the frequency spectrum of FM wave, that is, how the infinite sidebands are pictorially represented. So the diagram is something like this. If you observe, this is the central component, which is nothing but the carrier component. And on the right hand side, the first component, what you can see, it is the first sideband at a distance of FM. That means distance, what I'm telling is along this horizontal axis on which we are marking the frequency. So that means the first sideband has a frequency of Fc plus Fm. Now this is nothing but the upper sideband, and correspondingly I will have a lower sideband which is a mirror image at frequency Fc minus Fm. Similarly, I will have the second sideband with frequency Fc plus 2Fm and its mirror image at Fc minus 2Fm, and the third sideband at Fc plus 3Fm with its mirror image at Fc minus 3Fm. So this way the sidebands keep on continuing on either sides, and I will have infinite number of sidebands. As we move away from this central carrier frequency, observe that the amplitude of the sidebands are continuously decreasing. So as we move away to the other sidebands, maybe the 10th sideband or 11th sideband or 20th sideband and so on, what happens is the amplitude keeps on continuously decreasing further and further. And there is no point in transmitting all these sidebands which have negligible amplitude. So what we do is we consider only those sidebands whose amplitude is greater than or equal to 5% of the carrier amplitude, and only those sidebands are transmitted. So now getting back to our equation number 5, when we solve equation 5 using Bessel's function, the term what we get is something like this. So here, if you observe, this is a expression which has infinite number of terms. Here I have used some of the coefficients. They are J0, J1, J2, J3 and so on. These are the standard coefficients used in the Bessel's function, and they are called as the coefficients of 0, first, second, so on and so forth order of Bessel's function. The first component represents the carrier signal. So here you can see that in the first term J naught MF sine omega CT, it is nothing but only the carrier component. And as already told to you, it has infinite sidebands, each separated by a frequency of FM. The sideband frequency is symmetrical about Fc, and the fourth point that we observe is the amplitude of carrier and sideband depends on the Jn coefficient and also on the modulation index. Now, we will define what is modulation index. Again, students, please bear in mind this definition. It is one of the commonly targeted 1-mark question. Define modulation index for FM. So the definition is, it is defined as the ratio of maximum frequency deviation to the modulating signal frequency. That is, MF is equal to delta Fc max by Fm. Again, one of the very important formula that we will be using for solving the problems. Now students, here we will have totally around 5 definitions. The first one of course is for the significant sidebands, which we already discussed. The next definition, the second one, is the modulation index. The third definition is of bandwidth. Bandwidth of FM, as already discussed, is infinite, but practically it depends on the number of significant sidebands. So it is nothing but the width of the frequency spectrum that contains all sideband components with amplitude greater than or equal to 5% of the carrier amplitude. So in case if the bandwidth for FM is asked for 1 mark, the definition of bandwidth for FM will be the width of the frequency spectrum that contains all sideband components with amplitude greater than or equal to 5% of carrier amplitude. Students, you might observe some of the authors mentioning this 5% as 1%. There is a common representation of 5%, so I have taken this, but nothing wrong if someone is mentioning it as 1% also. This is the frequency spectrum diagram. So if you observe here, you can see that, say for example, if I consider there are two significant sidebands, so that time the frequency spectrum will be from this particular frequency to this particular frequency. So that time the total bandwidth will be nothing but equal to 4 FM. Moving ahead, the formula for bandwidth is 2n FM. If you remember, in the previous condition, I took two sidebands here. Coming back to the diagram, I told two upper sidebands and two lower sidebands will be the significant sidebands. So 2 into 2 FM, that is 4 FM. Generalizing this, we have the formula as 2 into n FM, where n is nothing but the number of significant sidebands. So the general formula for bandwidth is 2 into n into FM, where FM is the signal frequency. The bandwidth of the FM wave can also be calculated using another rule known as the Carson's rule. And according to this rule, the bandwidth is given as equal to 2 times the sum of delta FC, which is nothing but the frequency deviation, and the sum of it along with FM. We have already studied that MF is nothing but equal to delta FC max by FM. So cross multiplying this, we get delta FC as MF into FM. So we are doing that substitution here, and on simplification, we get it as 2 into FM into MF plus 1. We are just taking out FM common from both the terms, and the simplified expression is as shown below. So this is another formula for calculating the bandwidth of FM signal. Moving on to the fourth definition, it is a deviation ratio. So deviation ratio is nothing but the ratio of delta FC max to FM max. That means it is the worst case modulation index in which maximum permitted frequency deviation and maximum permitted audio frequency are used. So coming to this definition, here delta FC max is 75 kilohertz, and this value you need to remember it as it is very useful while solving the numericals. Delta FC has a different value when compared to delta FC max. This in detail we will be discussing when we are solving the problems. But as of now, please remember that for deviation ratio, when you have the formula as delta FC max by FM max, this value of delta FC max is equal to 75 kilohertz. Moving on to the last definition, that is percentage modulation. Unlike amplitude modulation, here percentage modulation calculation has a different formula. You represent it as a ratio of delta FC actual by delta FC max. Here delta FC actual is nothing but the particular value which is used for FM communication, and delta FC max is nothing but the value of maximum permitted frequency deviation, which as I told you before is nothing but equal to 75 kilohertz. Please do remember this. The value of delta FC max will be substituted as 75 kilohertz in two formulae. First one being deviation ratio and second one being percentage modulation. With this, we come to the end of today's video session. Till the next video, take care. Bye bye.